Math 1325, we are up to section 7.4 today. This is called the fundamental theorem of calculus. Fundamental theorem of calculus, which comes from finding areas under curves. And then if you do a definite integral means you're going to go from a to b, two given x values that you'll range between. The integral from a to b of a function, which is actually a derivative. So little f is you're starting with the derivative. This will equal the antiderivative. They denote it with capital F. So we previously had done indefinite integrals when there were no numbers here or here. And the integral of f of x dx is called the antiderivative. And they denote this big F of x. But in indefinite integrals, when you don't have numbers here or here, then you just put a plus c at the end. But the fundamental theorem of calculus says if you evaluate the antiderivative from a to b, that calculation will represent the area under the curve. And you go from the end minus the beginning, kind of like we did with those rectangle problems. So you go to the ending x value b first and minus the beginning one of a. So the antiderivative evaluated at b minus the antiderivative evaluated at a, that represents area under a curve. And we showed it both with geometry formulas and with a number of rectangles representing the area getting, the more rectangles you get, the better the approximation becomes. So the first 4 or 5 problems, you're just using this rule right here. Evaluate the definite integral from 0 to 4 for a function 7x squared minus 6x plus 8. And we did this previously without the numbers on the integral. So before it was just an indefinite integral. Now we're going to put from 0 to 4. So you can always tell when it's definite versus indefinite. If they don't put any values here or here, then it's an indefinite, and you just add a plus c at the end. But as soon as there's numbers here and here, now you're going to use the fundamental theorem of calculus. Get your antiderivative first, and then you're going to plug both of those into it. So if you go all the way back to section 7.1, we would have had this exact type of problem without the 4 and the 0 here. And then the rule for that is this is a polynomial, so you increase the exponent by 1 and divide by that new exponent. And you can just go term by term, do the same thing. 6x, increase the exponent by 1 and divide by that new exponent. Constants turn into linears. But instead of putting plus c here at the end, I'm going to evaluate this from 0 to 4. And if you want to reduce this first to a 3, that's probably better. 7/3 doesn't reduce though. So I need to do big F of 4 minus big F of 1. That's what the fundamental theorem of calculus tells us. Big F of 4 means I need to put a 4 in all 3 of these x slots. So there'll be a 7/3 times 4 cubed minus 3 times 4 squared plus 8 times 4. All of that is big F of 4. And I like to put brackets here, especially on the second half because of the minus right here. So plugging 1 in is nice because anything times 1 or to the power of 1 is 1. So plugging 1s into these 3 x's just makes the x parts disappear. And you literally get 7/3 minus 3 plus 8. 8 times 1 is 8. 1 squared is 1 times 3 is 3. And 1 cubed is 1 times 7/3 is 7/3. Okay, so 4 to the third is 64. 64 times 7/3 is not going to come out evenly. So usually what happens is you just do the 64 times 7, 448, and leave it over 3. 448 over 3. 4 squared is 16, times 3 is 48. 8 times 4 is 32. Then I'm going to get a minus 7/3, a plus 3, and a minus 8. You got to switch the sign of all the stuff in the second bracket. And you can add the regular numbers and you can add the thirds. Maybe the ones with thirds will reduce after I subtract them. So what's 448 minus 7? I'm doing 448 minus 7 and getting 441. Does that divide by 3? Yes, it does. So at least that part came out to 147. But if it was still over 3, I would have to leave it that way. So that's 147, and now I can minus 48, plus 32, plus 3, and minus 8. So this one will come out exactly to 126. That's what a definite integral is all about, is finding the antiderivative first and then plugging both values in. Minus 6 plus 8. Okay. Was it 0 to... Oh, it's 0 to 4, not 1 to 4. I don't know where I came up with 1. I guess I misread this here. This is supposed to be a 0. So 0 is actually easier because then all of these parts become 0. So all of this shouldn't have been here. So we are going to be stuck with a thirds here. So 448 over 3, we can't do anything with that. 448 doesn't divide by 3. 448 divided by 3 is a big, long, messy decimal, so they're not going to want that answer. So what you do is you do the regular numbers. If I do 32 minus 48, that's going to be negative 16. So I have 448 over 3 minus 16 over 1. So all you can do is get a common denominator of over 3. It's going to be 448 over 3 minus 48 over 3, which conveniently is 400 over 3. And that does not divide by 3, so you have to leave it like that. They prefer it in this format rather than a decimal. Never put a decimal unless they ask for it. And if they say simplified, they don't want a decimal. If they wanted a decimal, they'd say round to so many places. So 400 divided by 3. So I had a brain cramp mistake and misread my own handwriting and thought that that 0 right here was a 1. But at least you got to see how it could end. Sometimes these thirds parts do combine and disappear, and then you can get an integer answer, but sometimes it's over a fraction like that. So number 2, we're going from 1 to 9. This time it is a 1. 1 to 9. And then these square roots, I would change them to 1/2 exponents. So I have a 20y times the square root of y, or times y to the 1/2 is another way to write it. And then there's a 3 square root of y, so that's just 3y to the 1/2. And then you can combine this y would be 2 over 2 since it's 1. 1 is the same thing as 2 over 2. So I need to rewrite this one more time as 20y to the 3/2. 2/2 plus 1/2 is 3/2. When you multiply powers, you add their exponents. Okay, now we're ready to do the antiderivative. So you increase the exponent by 1. 3/2 plus 1 or plus 2/2 is 5/2. Divide by that same exponent. Move to the next term. Increase the exponent by 1. 1/2 plus 2/2 is 3/2. Divide by 3/2. And then instead of putting plus c, I want to evaluate this from 1 to 9. Although maybe we want to clean this up. If I multiply by 2/5, that would get rid of this messy fraction inside of a fraction. And 20 divides by 5 4 times. So I can actually get 8y to the 5/2 for that part. And if you multiply this by 2/3, the 3's will cancel after the entire bottom cancels. Then the 3's cancel. So it's 2y to the 3/2. And you're evaluating this from 1 to 9. So I need to do big F of 9 minus big F of 1. So 9, both 9 and 1 are nice because the half part of each of these fractional exponents is a square root. So you should do that first. So it's like you're doing 8 times the square root of 9 raised to the 5th power. That's what happens when you plug a 9 in right there. And then plus 2 square root of 9 for this part, square root of 9, and that would be to the 3rd power. So those two parts, that's big F of 9. Big F of 1 is easy because 1 to any power is 1. So if I do 1 to the 5/2 or 1 to the 3/2, they're both 1s. And times 2 and times 8 make them themselves. So it's just literally 8 plus 2 right here. So it's always nice if you can plug in a 1 or a 0 to either of these two slots. And that was the mistake I made last time, as I thought I had 1s, but it was actually 0, which was even easier than I was making it. So the square root of 9 right here is 3. But then you have to do 3 to the 5th power. 3 to the 5th power is 243. Then times that 8 in front. So 1944. Square root of 9 is 3. 3 cubed is 27. This is a cube right here. 3 cubed is 27. Times 2 is 54. And then you can either add this and get a 10 and just do minus 10, or you can do minus 8 and minus 2 if you'd rather do it that way. But it's 1944 plus 54 minus 10. 1988. So 1,988 units of area is what this represents. Okay, so we did a polynomial, we did fractional exponents. Now here are negative exponents. We're going to go from 1 to 3 on number 3. Three n to the negative 2 minus n to the negative 3. And n's the variable of interest, so that's why they're putting dn over here. So we know n, because if there was any other variable, even like x, that would be a constant in this case. So I'm ready to do the antiderivative. 3n, increase the exponent by 1. Negative 2 plus 1 is negative 1. Divide by that new exponent. Minus, increase this exponent by 1. Negative 3 plus 1 is negative 2. Divide by that exponent. And then instead of plus c, I'm going to evaluate this from 1 to 3. And we might want to clean this up first. So 3 divided by negative 1 is negative 3. And then I could put this n in the denominator and make it positive 1 because I'm going to be plugging numbers in. That would definitely be preferred. If I was just going to put a plus c at the end of this, then I would leave the negative exponent in the answer. But since I need to plug 1 and 3 in, it's better to have it not as a negative exponent. And then this negative 2 in the denominator, that's the same thing as positive 2 in the bottom. And then we could move that n to the -2 to the bottom and make it +2. If there's nothing left in the top, you have to put a 1. A top of a fraction can never be blank. So now I need to do big F of 3 minus big F of 1. Big F of 3, put a 3 right here. 3 divided by 3 would be 1, but then this negative would make it -1. Put a 3 right there. 3 squared is 9, times 2 is 18, so you'd get 1/18. This is big F of 3 right here. Minus, and 1s again are always nice. Plug a 1 in, and you get 3 over 1 is 3, so -3 for that part. Plug a 1 right here, and the n will disappear, and you'll just have 1/2. So I've got -1 plus +1/18 minus a -3 would be +3, and minus a half would be -1/2. I can easily add the 3 and the -1 and get 2, but the +1/18 and the -1/2, we'll have to leave these as fractions. So the easiest thing to do is make everything over 18. 18 would be the common denominator. Multiply this by 18 over 18, 36 over 18, plus 1 over 18, and multiply this by 9 over 9, and you'll get 9 over 18. 36 plus 1 is 37. 37 minus 9 is 28 over 18. Both of those divide by 2, so then we have to reduce it. 14 over 9. And they're always going to prefer these fractions, any kind of decimal. 14 divided by 9 is just a messy decimal, so they're probably not going to want that answer. Type an integer or a simplified fraction. See, so simplified, if you would have left it 28 over 14, they would have counted that wrong. 14 over 9. Now, say you don't like getting common denominators and doing all that I just did by hand. If you do have a graphing calculator, it can make things a whole lot easier when you get to the end of these problems. I could have typed into my graphing calculator 2 plus 1/18 minus 1/2. 2 plus 1 divided by 18 minus 1 divided by 2. If I type that in like that, there's that decimal that I just got from 14 divided by 9, 1.555555 repeating. And then if you hit math, enter, enter, it turns it into a reduced fraction of 14 over 9. So if again, the end of this problem from here down, this is all from previous math classes. When you get up to these higher level math classes, they expect that you know all the rules from the past and are like an expert at it, even though most students are not. So this part right here is a bunch of stuff from algebra and even pre-algebra. In high school and below, they teach fractions. So many people don't like fractions and are bad at them or make little mistakes while they're working with them. So, but that's not what this problem is really about. That's just how the ending of it goes. So if you had a graphing calculator, you could make that part easy, very easy on yourself, and just type it in there. And then the end of this problem is probably the hardest part for many students watching this video, but it can be the easiest part if you have a graphing calculator. You can go from being bad at combining fractions all of a sudden being an expert at it just by doing math, enter, enter. Okay, number 4. Now we got exponentials, and this will be a special case right here. Now, there are a few properties of these integrals, and you've seen a couple of them already. If there's a constant involved that you don't need, you can pull it out front. So when I have this 0.3 e to the negative 0.3a, if this 0.3 doesn't help me do the problem, then I could just pull it out front and ignore it till the end. So it may or may not help to have this 0.3 here. If it's not, then we put it out there. That's that mistake I made on that number 10 problem. We had an extra constant here that wasn't needed, so I was supposed to just pull it out front, not put 1 over it. And then another thing is if you have addition or subtraction going on, kind of like a polynomial with multiple terms, you can do separate integrals for each part that's added or subtracted. Sometimes that's helpful if you get different cases going on, like this is exponential, and this is a different special case, 4 over a. So I can just do these separately. I should put a dA here, though. I can do each one of these separately, just they might have their own rules where it helps to think about them separately. Now, I'm noticing right now this one says round to 3 decimal places. The reason they're going to take decimals here is because of the E. E is always going to be a decimal, and you could leave E in the answer, but for whatever reason they want a decimal here. This is when you do a decimal is when they ask for it, but this is only when you do a decimal. Okay, so this first part right here, this is like section 7.2. I can do a U substitution here. And I'm going to let, whenever there's exponentials, usually the best strategy is let the exponent be the U substitution. So I'm just going to let negative 0.3a equal U. The derivative of that would be the constant in front, negative 0.3. Because the derivative of a linear is just a constant. And then because a is the variable of interest here, there would be a dA over here. Well, I almost have that. I have the 0.3 and the dA. I don't have the negative, though. So I almost got what I needed, but there's an extra negative here. It's like there's an extra negative 1 here. So I need to insert a negative 1 there, and I can only do that if I do a 1 over negative 1 on the outside. That's where you need it on both the inside and the outside. When there's an extra thing in the du part, that's when there's something on the outside that's going to happen. So in essence, I'm just creating a double negative. A double negative is the same thing as a positive. So by putting a double negative here, I'm not changing the original problem. But then this negative will be on the outside. This negative 0.3 is what's needed to have the du happen. And then I can have e to the u du. And now that's very easy to evaluate. The integral of e to the u is e to the u. And then if I was doing an indefinite integral, I would just put plus c here and then change the u back. But since I'm going to be doing a definite integral, then first we're going to substitute what u was back in for that slot right there. So I've got a negative e to the negative 0.3a. And then I'm going to evaluate this from 2 to 3. And then now the rest of this is like what we've been doing in this section, but we had to go back to a previous section first to get all the way to that point. This is a separate case that doesn't need a u substitution. The integral of something over a, well, actually I should say 1 over a. So maybe here's a case where I do want to pull the 4 out in the front and forget about it. That extra 4 isn't needed. But this is its own rule right here. The integral of 1 over a, remember that one? That's the natural log of the absolute value of a. Plus c potentially, but instead I'm going to evaluate it from 2 to 3. And because both 2 and 3 are positive, then the absolute value doesn't matter. So I can just do 4 ln of a from 2 to 3. So sometimes that absolute value disappears if you know you have all positives going on. Okay, so I'll have to do big F of 3 minus big F of 2. I'm going to have to do this twice. I have to do it for this part, and then I have to do it again for this part. Which the second part's actually usually easier. In fact, it is easier here. But I'm doing 2 separate problems at once that are added together. So negative e to the negative 0.3 times a, but plug 3 in for a. So I'm going to have negative e to the negative 0.3 times 3. That's big F of 3. Minus big F of 2, which is negative e to the negative 0.3 times 2. Now, I put some brackets here and here because I know there's another part coming. But normally, if they hadn't put a plus right here, if there hadn't been a second half to this problem, this first half could have been the entire problem. And then big F of 3 minus big F of 2, we would be done right at this point as soon as we're done calculating all this. And if you remember before, I would put a bracket around big F of 3 and then minus big F of 2. And you can do that if you want. But anytime there's just one thing in each part, then I don't put extra brackets there. So if the entire problem was just this, I wouldn't have any brackets at all. I would just write negative e to this minus negative e to that, and I wouldn't put any brackets. So maybe here the brackets are getting a little confusing, but okay. But anytime big F of 3, if you just plug it into one single item, then you don't really need any brackets unless you want to put them. So negative e to the negative 0.9 is what that part would be. And then this minus a negative can turn into plus e to the negative 0.6. So whatever this calculates to as a decimal, and I don't know if we need to do it yet or we're going to have to do it eventually anyway, negative e raised to the negative 0.9 plus e raised to the negative 0.6. I can just get a messy decimal for that. And they want it rounded to 3 decimals, so I'll put 4 for now. 0.1422. That could be the end of the problem if there hadn't been this second part to it. So just because there was a second part, now I have to do this all over again. F of 3 minus F of 2. You normally don't do this twice, but we're doing it twice here because we had 2 completely separate integrals, really. But this part's not hard at all because it's just 4 times ln of 3 minus 4 times ln of 2. You're just going to plug 3 and 2 in there. So I can have 4 ln of 3, that's literally f of 3 right there, minus 4 ln of 2. And here I'm not putting any extra brackets just because each one's one part only. I have this outer bracket just because this is a second case completely separate from that case. But I can even drop the brackets now and just have this. So 4 ln of 3, 4 ln of 3, that has a decimal of 4.3944. 4 ln of 2 has a decimal of 2.77258. I'll bump that up to 26. So 0.1422 plus 4.3944 minus 2.7726 is 1.7636. Now we're going to round to 3 decimals, so 1.764. But only because they asked for decimals. When you get LNs and E's, then we could leave the answer like this, actually. If they said give me an exact answer, we would just leave it like this. But it's kind of messy to look at that. So in some really messy cases, even when the exact answer is messy, then that's often when they'll accept decimal answers. But don't put a decimal unless they ask for it. 1.764. Okay, now we're going to go from -1 to 0 for y times 4y squared minus 3 to the third power dy. Here they are again. We're on number 5 now. I thought we were on 4. Okay, 5. Here they are again reviewing something from the past. This is section 7.2 at the beginning of this. Because I have what looks like a product rule or even maybe a chain rule. So there's no way to do this integral directly. So here's where you have to use substitutions again. I'm going to let u equal the inside of the parenthesis. Whenever there's a parenthesis to a power, the inside is usually the best u substitution. And then the derivative of that turns out to be 8y to the first plus nothing. And I have an extra 8 over here. There's an extra 8 in the du that the original problem doesn't have. So that's when, if you want to put the 8 here because you need it, you can do that, but only if you put a 1/8 on the outside. If the 8 was extra here, then I would just pull it out front. That's the two cases that can happen. So watch out for that because I messed it up a couple of sections ago myself on that last problem. So you got to pay attention. Where's the extra 8? If there is an extra 8, is it in the du part or was it in the original problem? That makes a difference. If it's in the du part, you have to put a 1/8 out front. If it's in the problem itself, you just pull the 8 out front. So now I have 1/8 as an outside constant. And then this parenthesis part is u to the third power. And everything else is du. That's the whole point, is to get everything else covered. 8y dy, that's what du is. So then I have an easier problem to work with. Now I can do the antiderivative much more easily. Here's the constant we can do at the end. Increase the exponent by 1 and divide by that new exponent. And then normally plus c, but I'm going to plug the u stuff back in first. So this is 1 over 32 u to the fourth power. But I'm going to plug in 4y squared minus 3 back in for u. And that way, when I get it back to y instead of u, now I can evaluate it from -1 to 0. You don't want to evaluate from -1 to 0 with u as the variable. It wouldn't be the same numbers there. So plug that stuff back in for u before you do any evaluating. So now we're ready to do big F of 0 minus big F of -1. That's the fundamental theorem of calculus now. And big F of 0, sometimes the answer to that is just 0, but here it won't be, because when I plug 0 in right here, 0 squared is 0, times 4 is 0, but 0 minus 3 is -3. And -3 to the fourth power is actually 81. So you would get 81 over 32 for that part. And that entire answer is big F of 0. I don't need any brackets because it was just one thing, really. You can put brackets if you want, but I just put the brackets when there's like multiple terms that I'm plugging the 0 into. If there's only one y to plug into, then you don't really need brackets for that. So same thing here, minus. Now I'm going to plug -1 in. -1 squared is 1, times 4 is 4, minus 3 is 1, and 1 to the fourth power is 1. 1 times 1 over 32 is 1 over 32. So now I have 81 over 32 minus 1 over 32, which is 80 over 32. And both of these divide by 2, they divide by 4, they divide by 8, I think they even divide by 16. But if you don't know that, you can always do 80 divided by 32 in here. And whether you press equals to get the decimal version or just leave it as a fraction, math, enter will reduce it if it reduces. So it reduced it all the way to 5/2. So 80 divided by 16 is 5, and 32 divided by 16 is 2. So that's why it reduces to 5/2. If I would have done 80 divided by 32 and got 2.5 first, then I can hit math, enter, and it also makes it 5/2. So it doesn't matter if you make it a decimal first. And because it's exactly 2.5, maybe they would take that answer, but you definitely don't want decimals if they're long, repeating, messy decimals, or even just some messy decimal. Here it says type an exact answer, but 2.5 is exact, so I'm curious what they take. Sometimes they count decimals wrong no matter what, but it was exactly 2.5. Clearly they'll take 5 over 2, but will they take 2.5? This is one nice thing about the homework, is you can try things and see if they take it in the homework, then you know you can do that on a test. So here they would take 5/2 or 2.5. I don't think they would take 80 divided by 32 because it does say simplify the answer, so that would not be considered simplified. Okay, one more of these. This number 6 will be the halfway point of this assignment. Here's another one where we have to do a U substitution because we have what looks like a quotient rule or even a chain rule going on. So there's no way to do these complicated ones directly. You got to use U substitutions. But at least this is a good review of section 7 too, also at the same time. So an integral from 1 to 4, there's an x in the denominator, and the numerator has an ln, 18 ln of x to the 5th power. And the ln of x, the whole thing is to the 5th power, not just the x. It could be just the x, but here it's the whole thing. Well, this 18 might turn out to be an extra constant entirely, or even a partial extra constant. So if this is extra, I can just pull it out front. But I need to see if it is extra or not first. So I'm going to let the inside of this parenthesis, what has an exponent, let that equal u. And conveniently, the derivative of that is 1 over x. And that's why there's an x down here. So it is true that this 18 is an extra constant. That's an extra constant in the problem, not an extra constant over here. So that's the mistake I made on that problem number 10, is I should have just pulled that out. Actually, it was kind of a hidden extra constant. There is why I missed it. There was actually a 500 here, and then the extra constant was part of a fraction, so that made it real confusing. I wasn't paying attention at that point to where it was actually located. So keep track of that. Where's your extra constant? If you have one, is it in du? Then you're going to need a 1 over it out here. But if it's in the problem, you just pull it out front. So I can think of this divided by x as 1 over x. And then I have ln of x to the 5th power. So the 1 over x and dx, that is du. And this is u to the 5th power. But now I have a much easier antiderivative to do. This is just a straight polynomial that works out with the power rule. So you increase the exponent by 1 and divide by the new exponent. And then after I plug the stuff back in for u, then I can evaluate it from 1 to 4. But don't try to evaluate it from 1 to 4 right now. 18 divided by 6 is 3. I'm going to plug the stuff back in for u, plug ln of x back in for u to the 6th power. Now that I'm back to the variable x, now I can evaluate this from 1 to 4. So big F of 4 minus big F of 1, there won't be any need for brackets because it's just one term per part. So I'm going to plug a 4 here, and then I'm going to plug a 1 here. 3 ln of 4 to the 6th power. That entire part is all f of 4. And then minus 3 ln of 1 to the 6th power. I'm guessing they're going to want decimals here because ln of 4 is just a messy decimal. Now ln of 1 is actually 0. Any log of any base of 1 equals 0 because every log graph goes through the coordinate 1, 0. So this part is 0. 0 to the 6th power is 0, and 0 times 3 is 0, so the whole second half is 0. And if you didn't know that, ln, whoops, okay, this calculator, I guess you have to put the 1 first. 1 ln. ln of 1 is 0. But ln of 4 is a big messy decimal. And then we need to raise that to the 6th power. And then multiply by the 3 in front. So they probably want this rounded, round to 3 decimals. Whoops, where's my calculator? Here it is, 21.2938. So we have to add 1 to the 3 and make it a 4. 21.294. Minus 0 is 21.294. 21.294. Okay, so the first 6 problems were all just doing definite integrals in general. Now we're going to move specifically to area. And this will happen on the next 4 problems, and I think the last 2 are these business application problems. But what's happening next is, if I do an integral from the start of this graph to the end of this graph, if I go from x of 0 to x of 3, I could just do that with this function. If you do an integral from 0 to 3, an integral from 0 to 3 of 4 minus x squared, you'll get some kind of answer like we've done on the first 6 problems. But the issue is, if you want to really deal with actual area, like geometrical area, area by rule in geometry or in any other math subject is positive by rule. You can never have a negative area. Your house, like the square footage of your house, can't be negative. So area by rule is always positive. Well, it turns out when you do definite integrals, you're really going from the curve to the x-axis. And if your area is entirely above the x-axis, then the integral answer will agree with the actual area. In other words, they'll both be positive. So say that this has an area of 20 right here in this top part. If I did an integral from 0 to 2 of this function and did all the calculations, big F of 2 minus big F of 0, that would equal 20. But it turns out if you do one below the x-axis, you actually get negative whatever it would have been. And it's because you're doing an integral of the x-axis minus the curve instead of the other way around. And another property of integrals is if you ever do it, well, 2 different properties. If you reverse these 2 numbers, that also causes the answer to be negative. You'll get the negative answer of what you would have got the other way if you reverse those 2 numbers. Or if you do the original numbers, but if you do the negative version of the problem, and that's what's in essence happening when the graph's below the x-axis, is you're actually doing the negative version of the function. So therefore the answer comes out negative. So let me do this number 9, 6, 7, 8, 9. This is 9. Let me do this one first because it's a little easier to see that they did the graph for you. When we go back to number 7 and 8, we have to do the graph ourselves. But that's the key to doing these, is if you're actually talking about area, not definite integrals, the representation of them is area. But if you do a definite integral, if they just say find the definite integral like 1 through 6 said, then they don't care if some of the area is negative actually. Evaluate the definite integral. You don't need to worry about does it go below the x-axis or not. But if there are parts that go below the x-axis, they actually contribute negatively to the answer. And that's okay here. But as soon as you switch to find the area, if they mention the word find the area, then you can't get any negative parts to your answers. And then what happens is you have to look at the graph and find any spots where it crosses the x-axis, if any. And if there's parts above and below the x-axis, you have to calculate these separately. So I need to do an integral from 0 to 2, the part that's entirely above the x-axis, for 4 minus x squared. And then I need to do a separate integral that goes from 2 to 3. Instead of doing it all from 0 to 3, I have to do these separately. And this part is going to be negative. I can tell already based on the picture. Based on the graph, this is going to have a negative answer to it. So I can expect that to happen and then be ready for it. And the one good news is this is the same in both parts. So when you do the antiderivative, you don't have to do it twice really. The antiderivative of 4 is 4x, because that's a constant turning into a linear. The antiderivative of x squared is x to the third over 3. Evaluate this from 0 to 2. Big F of 2 minus big F of 0. Big F of 2 would be 4 times 2. Now here's where I am going to put a bracket because there's two different x's. So big F of 2 is going to have two parts to it. 4 times 2 is 8. This minus right here, 2 cubed is 8 over 3. Then this minus is different than this minus. Big F of 0 is 4 times 0, which is 0, minus 0 cubed over 3 is also 0. So often when you do big F of 0, you get all zeros off in here, but we had one earlier that wasn't. So whatever 8 minus 8/3 is going to be the first answer here. And this is where this could help if you do 8 minus 8 divided by 3. Math, enter, enter. It's 16 over 3. So there's a positive 16 over 3, which is about 5.3. There's about 5.3 of positive area right here. And clearly, if this picture is drawn to scale, clearly this seems to be a larger area than this little segment. But this little segment's going to be negative something, and I'm guessing a little less than negative 5. But now the nice thing is I don't have to repeat the antiderivative. It's still 4x minus x squared over 3. I don't have to recalculate it from scratch. But I need to evaluate it from 2 to 3. So now we need big F of 3 minus big F of 2. Big F of 3 would be 4 times 3, 12. And 3 cubed is 27, which divided by 3 isn't exactly 9. That one came out nice. Now big F of 2, 4 times 2 is 8. And 2 cubed is 8 over 3. In essence, this bracket right here is the same as that one right there. It's just that there's a minus in front of it. So now you're going to get 3 minus, this we already know is 16 over 3. But 3 minus 16 over 3, 3 minus 16 over 3 is negative 2.333. See how it's negative? Math, enter, enter. It's, whoops, negative 7/3. Because it's below the x-axis. Anytime the area is below the x-axis, the calculation itself has to be negative. If I would have just done an integral from 0 to 3, just one single interval from 0 to 3, of 4 minus x squared, I would have got 16/3 minus 7/3. It would have been 9/3 or 3. The total area would have been 3 if I would have just done one big integral from the start to the end. But that doesn't really represent positive and negative area properly. So what you do instead is, you're not doing 16 over 3 minus 7 over 3. Once you get, if they ask for area, once you get a negative area, then you just automatically switch that to positive if they ask for area. If they would have said, find the definite integral, I would have got a different answer here though. So 16 over 3 plus 7 over 3 is 23 over 3. So integral from 0 to 3, I can tell that this answer would have been, it would have been 16 over 3 minus 7 over 3, just like it looks, which is 9 over 3 or 3. If we would have done this like the first 6 problems, we would have got an answer of 3. But if they ask for area, then you have to do the parts separately, and any part that comes out negative, you switch to positive. And then you add all separate areas together, just like in geometry. Remember those geometry problems where they would say you want to paint a garage, and then there's like a triangular part where you're going to put a basketball goal maybe. So you want to paint this triangle part, and you want to paint the garage door. How much paint do you need to buy? So you did area of a rectangle, and then you did area of a triangle, and then you added these together. Whenever you're doing separate areas in geometry, you add them together. So 23 over 3 is going to be the answer here, which is like 7.6666. So instead of getting an answer of 3, you're getting an answer of over 7. If you want to talk about actual area, not just combined area. So again, focus in on the x-axis. If they ask for area, make sure they're asking for area. They're not just saying do the definite integral. So if they ask for area, I have a below area that's going to come out negative. I have above area that's going to come out positive. And then I need to, once I get this negative answer, I'll switch it to positive, and then I'll add the two results together. So I need an integral from 2 to 3 first of this function, then another integral from 3 to 4 of this function. The first answer will be negative, the second answer will be positive. I'll switch the first one to positive and add them together. So from 2 to 3 for e to the x minus 2 plus e, that's going to have a negative answer to it. I can already tell because of the graph is showing that it's entirely below the x-axis. Then if I go from 3 to 4, this will have a positive answer for sure. Now, if this was something more than x minus 2, you would have to do a u substitution. But since it's just x minus 2, the derivative of 1x minus 2 is 1. So then the chain rule is not really applying here. So the integral of e to the x minus 2 is itself the same way the derivative of that is itself, because by the chain rule, the derivative of the exponent is 1. The antiderivative of e is, see, that's just a constant here because x is the variable of interest. So the derivative of that's linear, ex. The same way the antiderivative of 4 was 4x. The antiderivative of e is ex. And then we're going to evaluate this from 2 to 3. And then luckily we'll get the same exact antiderivative. And we'll evaluate that from 3 to 4. This answer should be positive. This answer should be negative. And then we'll know we did it right if we get that. So big F of 3 minus, see the fundamental theorem of calculus has a minus here. This can have a plus or a minus in it, but this is always minus no matter what here. Big F of 3 minus big F of 2. This one's going to be big F of 4 minus big F of 3. So if I plug 3 in, and I have to plug it in 2 different x's, so that's, I'm going to put a bracket. E to the 3 minus 2 plus e times 3. That's big F of 3 right there. Minus big F of 2 would be e to the 2 minus 2 plus e times 2. E to the 3 minus 2 is just e to the 1. E plus 3e is basically what you're getting there. E to the 0, 2 minus 2 is 0. E to the 0 is 1, but then you have to put the negative on it, so it'll be negative 1. And this positive 2e will turn into negative 2e. So I've got a 4e minus 2e, which is 2e. 2e minus 1 is what this whole answer is. And that doesn't make sense because it's not negative. 2 to 3 should definitely be negative. E to the x minus 2. What that says. Or maybe that's a plus. Maybe I can't tell if that's plus or minus. But plus would make it even more positive, I think. I think that is a minus. Okay, so e to the x minus 2 is itself. Derivative of that would be itself, and it would just be e, yeah. Big F of 3 is 1. 3e. Big F of 2, 0 is 1, negative 1, and negative, that's strange. I didn't get a negative for that part. Well, let's see what happens on this one. So e to the 4 minus 2 would be 2, plus this part would just be 4e. And then e to the 3 minus 2 is e to the 1 plus, maybe that's where I made a mistake. Is there a minus there? Oh yeah, that's what it is. See, there's a minus right there. So I have another brain cramp mistake right there. This should be minus, not plus. I wrote the problem down wrong. But see, I could tell something was wrong because this shouldn't have happened. So this should be minus, which means this part is minus. This should be minus, so this part would be plus. So I actually have a 3e minus 3e, which is 0, so this whole part is just -1 actually. That makes more sense there. So this has an area of -1 on its own, but then if I'm really talking about area, I'm going to switch it to +1. So the first calculation comes out to -1 if I would have had the minuses in the right spots. There, let's correct it now. So here we have e squared minus 4e. And then we're going to get a minus e. And then this should be minus at first. But then I'm plugging in 3, so 3e. And then the minus and negative will turn that into plus 3e. So we would get an e squared. This is minus 5 and plus 3, so minus 2e. But e squared minus 2e is definitely positive because squaring something makes it bigger than multiplying it by 2. And now we need to see how they want the answer, decimals or not. Type in an integer or a decimal rounded to 3 decimal places. Okay. So this is -1, but we're going to switch it to +1 because they want area. And then this should be positive some decimal. E squared minus 2e. E squared minus 2e. I don't think I did that right. Let me do it here. E squared minus 2e. Yeah, didn't do it right there. So I got 1.9524. So rounded to 3 decimals, that would be 1.952. So the lower area is -1. The upper area is positive almost 2. And in the picture, it appears that way too, that the upper area certainly seems bigger than the lower area does. So that kind of makes sense. But then if I really want area, then I have to take this -1 and turn it into a +1. So I turned that into +1, and now I add the separate areas and get 2.952. And again, this should have been minus right here. I wrote the problem down wrong. 2.952. But if you pay attention to which part should be positive, which part should be negative, then you can avoid brain cramp mistakes like I almost had. Okay, so let's go back to 7. 7 and 8 are just like 9 and 10, except you have to draw the graph yourself and figure out what parts are above the x-axis, which parts are below. So I have an 8 minus 2x squared. That's a parabola. And we want to go from 0 to 4, and it does say find the area, so then I have to watch out for negative areas. If they just said find the definite integral, then I wouldn't care about negative areas. So the function is 8 minus, let's make sure I write it down right this time, 8 minus 2x squared, and go from 0 to 4. But I'm not just going to blindly go 0 to 4 and do the whole thing. I need to draw a graph of this and make sure that if it is going to go from 0 to 4, it better be all above the x-axis. So 8 would be the y-intercept. And if you're negative, the parabola goes downward. 2 makes it vertically stretch by a factor of 2. If I plug 1 in, and really I don't even care about the negative side here, so there's 0. When x is 0, y is 8. If I plug 1 in, 1 squared is 1, times 2 is 2. 8 minus 2 is 6. So when x is 1, we're now at 6. When x is 2, 2 squared is 4. 4 times 2 is 8. 8 minus 8 is 0. So by 2, it's already on the x-axis. And it's going to keep going down, so that tells me the rest is going to be below the x-axis. So, but I do need to know what is it? Do I need to know that or not? I guess not. But 4 squared would be 16 times 2 is 32. 8 minus 32 is negative 24. So this would keep going down. And when it reached this point, it would be at 4 negative 24. It really doesn't matter for us as long as we know that's happening at 4. So I've got this area right here that's above the x-axis. From 0 to 2, you're above the x-axis, so I have to do an integral for that. From 0 to 2, this integral is going to have a positive answer. And then I have to do another one from 2 to 4 of the exact same function, but this will definitely have a negative answer to it. So at least these antiderivatives are easy. The antiderivative of 8 is 8x. And unfortunately, this one doesn't come out nice, but increase the exponent by 1 to a 3, and then divide by 3. So you'll get 2/3 x to the third. This one's going to get evaluated from 0 to 2, and it should come out positive. This one, you're going to get the same antiderivative, but you're going to evaluate from 2 to 4, and it'll come out negative. So big F of 2 minus big F of 0. Big F of 2 is 8 times 2, 16. There's a minus here. Then plug 2 in here. 2 cubed is 8. 8 times 2 is 16 over 3. Those two parts are big F of 2. Now there's always a minus here because that's the fundamental theorem of calculus. Big F of 0, if I put zeros into these x's, they're both going to be zeros, which is often the case, but not always. So if the whole second part, F of 0, is all zeros, then this part doesn't matter. So whatever 16 minus 16 divided by 3 is, math, enter, enter, it is 32 over 3. That's what this top area is. This top area is 32 over 3, and it is positive. So now we're going to do this bottom area, which should be negative. And because it goes down farther than this one goes up, it should be a more negative than the other one is positive. So there are ways by looking at the graph to kind of know what to expect. And that way, if you make a tiny mistake like I almost did, when I changed a minus to a plus accidentally in the original problem, then if you make a mistake like that, you can sometimes know it's wrong before you even go putting the answer in. So now we need big F of 4 minus big F of 2. Big F of 4 is going to be 8 times 4, 32, minus 4 cubed is 64, times 2 is 128 over 3. Minus big F of 2 are these two things right here. 16 minus 16 over 3. So I've got 32 minus 128 over 3 minus 16, but then plus 16 over 3. And the easiest thing to do is put it in a graphing calculator and hit math, enter, enter. Then it'll be real easy. 32 minus 128 over 3 minus 16 plus 16 over 3. See, it's negative 21.3 approximately. The other one was about 10.6 approximately. So there is almost twice as much. Negative is positive. But math, enter, enter makes it negative 64 over 3. If I would have just done a straight integral from 0 to 4 of the entire function, it would have been 32 over 3 minus 64 over 3. The answer would have been negative 32 over 3. But instead, that would be the integral. Instead, I'm going to take 32 over 3. Instead of minus 64 over 3, I'm going to add 64 over 3. If I want area, actual area. The actual physical area is 96 over 3, which actually reduces 96 divided by 3 is exactly 32. So there's 32 total units of area if I ignore the negative portion that's below the x-axis. But if I included that as a negative, then the answer would have been negative overall, actually. $32. And here's another one. 2x cubed is the original function. We're going from -3 to 5. $2x cubed from -3 to 5. Well, the x cubed graph, even if you multiply by 2, is just a vertical stretching. It's going to be like this. So wherever -3 is, you're going to have a bottom area below the x-axis that's negative, and then wherever 5 is, you're going to have a positive area here. So that 0 is the spot where it crosses the x-axis. So I need an integral from -3 to 0 for the 2x cubed, and that'll have a negative answer for sure. Then I can add the separate area from 0 to 5 that will have a positive answer. And each one of these just has one part to do. The antiderivative of 2x to the third is 2x to the fourth divided by 4. Or 1/2 x to the fourth. And first you're going to evaluate it from -3 to 0. Then you're going to evaluate it from 0 to 5. The first answer should be negative. The second answer should be positive. That'll be my double check. And once I get the negative on this part, then I can switch it to positive. So big F of -3. No, you do the ending first. Big F of 0 minus big F of -3. This should be negative. And in fact, it will be, because 0 to any power is 0, times 1/2 is 0. The front half of this is 0. And 0 minus something is going to be negative. So the -3, if you plug that in, -3 to the fourth power is positive 81. So you get 81 over 2. But it's 0 minus 81 over 2, which is negative 81 over 2. So this bottom area is negative 81 over 2, which makes sense that it's negative. But then if I care about actual area, then I'm going to switch it to positive 81 over 2. If I just cared about a definite integral, I would leave it as negative. And now do big F of 5 minus big F of 0 over here. And we already know big F of 0 is 0. So this one's going to end with minus 0. 5 to the fourth power is 625. So that's 625 over 2. So the upper area has a positive 625 over 2 area. If I did an integral all the way from -3 to 5, it would be negative 81 over 2 plus 625 over 2. But if I do area, then they're both positive. And I'm going to get 706 over 2. '81 plus 625, yeah, 706 divided by 2. So the total area is 353. But the key thing to doing problems 7, 8, 9, and 10 is finding where does it cross the x-axis so that you can get your separate areas going. And any portion that's below the x-axis will have negative answers. Anything with above the x-axis will have positive answers. But any negative answer that comes out, if you're doing area, you switch it to positive and add it to the positive areas. Okay, then we got our two business type problems. Here it is the rate of profit. So they're giving me a derivative function, and they want me to find total profit for the first 3 years. That's the regular version. That's the antiderivative. So if you're starting with a derivative, then the antiderivative will bring you back to the original. Oops, I was going to put number 9, but this is actually number 11. So the derivative of profit, the marginal profit, is 5t plus 20 t squared plus 8t plus 1 and that has an exponent, 1/5 power. I have two different functions of t multiplied together. That looks like a product rule, and this is kind of like a chain rule with an exponent here. So if I do they want it for the first 3 years. First 3 years means you're going from 0 to 3. If I do an integral for the first 3 years, 0 to 3, of this derivative function, it will turn it into regular profit instead of marginal profit. And this we need a u substitution for. And I would let the parenthesis part that has an exponent, that's always the best substitution to set equal to u. If I set the parenthesis part equal to u without the exponent, the derivative of it may equal what's already here or be some constant of it. So this is 2t plus 8. So it didn't equal 5t plus 20 exactly, but maybe we can multiply something by it to get it to come out. It's unfortunately going to be messy, but the best way to do it is say something blank times what I have needs to equal what's there. So what times 2t plus 8 is going to equal 5t plus 20? What could I make have that happen? And really, you could do this individually, like what's going to make the t's work, what's going to make the numbers work. So if you had, like, let's just do the number 8 times something equals 20, what's the something? 8 times what's going to get me up to 20 because it doesn't come out exactly. And then I can just double check that it is the same value for the t. So that's 10 over 4 or 5 over 2. 5 halves times 2t plus 8 is 5t plus 20 because 5 halves times 2t, the 2's cancel, and that's how you get 5t. And 5 halves times 8 is clearly 20 because that's how we figured it out. So my du is short by 5 halves. I need it to be 5 halves. I need there to be a 5 halves here in order to make this happen. So this is actually, see what I have here is this is 5t plus 20 is what's actually here. But 5t plus 20 is equal to this. So I could write it this way. And this one's tricky because it's fractional. But if this was the original problem, then I would have everything I need. I would have this and this making the du happen. This would be u to the 1/5 power. And then there's an extra 5 halves, but this is where it's easy to mess it up like I did at number 10. This extra 5 halves is not over here. It's not here yet. It's an extra 5 halves in the original problem itself, even though it's hard to know that. So that's where you just move it to the outside. There is no 1 over going on here. So I have a 5 halves extra constant out front. This part equals u to the 1/5. And by pulling the 5 halves out, then the rest equals du. So the antiderivative of that is u to the, add 1 to this, 1/5 plus 5/5 is 6/5. Divide by 6/5. or multiply by 5 over 6 to make that cancel. So the antiderivative is 25 over 12. Now I'm going to plug the u stuff back in. T squared plus 8t plus 1 to the 6/5 power. And then I need to evaluate this from 0 to 3 to finally get the part A answer. This problem is really messy with all these fractions. One nice thing is the 0 part. This will be 0, this will be 0, but there'll be a 1 there. But 1 to any power is 1. And 1 times 25 over 12 is 25 over 12. So when we do big F of 3 minus big F of 0, the big F of 0 part is just 25 over 12. It's not 0, but it's 25 over 12. Big F of 3 is going to be harder. So plug 3 into the parenthesis. 3 squared is 9. 8 times 3 is 24. 24 plus 9 is 33. Plus 1 is 34. 34 to the 6/5 power probably doesn't come out exactly. 34 to the 6 divided by 5 power. See, it's a big messy decimal. But then times 25 over 12. Still a messy decimal. They probably want this rounded somewhere. Round to the nearest dollar, okay. So I have 143.3 to the nearest dollar, that's 143. 25 divided by 12 to the nearest dollar is 2. But I wonder if I should do minus 25 over 12. Just do it in here first. And round this to the nearest dollar. It would be the same, yeah. So even if you round 25 divided by 12, that's 2 point something. So that's rounded to the nearest dollar is 2. 143 minus 2 is $141. And it might be like in thousands of dollars. Okay, round to the nearest dollar. So over the first 3 years, they made 141. Okay, this could be a slight issue. Let me put this in first. 311. No, okay. Round to the nearest dollars. 34 did that times 12/5. Do they want it just to the 1,000? No. 312. Huh, that's weird. Okay, I had 141, 311, and they had 312. But if the next digit's not 5 or higher, you shouldn't add 1. I don't know why they're making that 312. To me, it should stay 311. So I first put 141, 311, but they counted that wrong. Then I wasn't sure how they wanted it, but now that I see the answer, I can tell that's what they did want, but I'm wondering why they rounded that up when it shouldn't round up. Round to the nearest dollar doesn't say round up. That's strange. Okay, so then, see, total profit, that's antiderivative. Regular profit for the 7th year, you just plug 7 into your antiderivative. So where was my antiderivative? It's right here. So the derivative function, or the regular function, is this. The profits are 25 over 12. 25 over 12. T squared plus 8t plus 1 to the 6/5 power. This is what we got for our antiderivative. So in part B, they want you to do this for the 7th year. In other words, just plug 7 into the, not into the derivative function, into the regular function. So 7 squared is 49. 8 times 7 is 56 plus 1. 49 plus 56 plus 1. Whoops. 49 plus 56 plus 1 raised to the 6/5 power times 25 over 12. So, and again, this is in thousands of dollars. So I got 561.2105. So the nearest dollar should be 561.211. This time I would say it does go up 1. Because when you get this, if you multiply by 1,000, that's how you can turn it into thousands of dollars. 561.210, but after that's a 5, so it should be 211. This time I would say it does round up. And they're not doing that, okay. The profit for the nth year is given by the definite integral. Okay, so maybe, okay, I was wrong about that. You don't just plug it in to the original function. It's another definite integral, apparently. So we were supposed to do from the start of the 6th year to the end of the 7th year. Well, it doesn't make sense that that would be total profit for the 7th year. Okay. And we already did the antiderivative, so that's right here. So this would have been the derivative function here. So then I would get this. To the 6/5 power, and then I need to evaluate it from 6 to 7. So it's big P of 7 minus big P of 6. And the 7 is the one I did already. Okay, so I just did the 7th one is what's wrong. So the 7th one was 5, 6, 1, 2, 1, 1. And then if I redo it for the 6th one, okay, so 6 squared is 36. 8 times 6 is 48 plus 1. Raise that to the 6/5 power. And then times 25 over 12. Times by 1,000 to turn it into thousands of dollars. So that's 430,587.5. So that's going to bump up to 8. And then let me see if it makes a difference if I round both of those now versus doing them later. If I round them both now, it's 130,623. If I would have left it 561,210.5 minus 430,587.5, does that make a difference? No, okay. So 130,623. And that's closer to that first answer anyway. 130.6, not point, but 130,623. Okay, so that's, so for part A, you're going from 0 to 3. For part B, you're going from 6 to 7. If they want the 7th year, you just go from 6 to 7. First 3 years, you go from 0 to 3. I still don't know why that's a 12 and not an 11. Because I first got 141, 311, but they're saying it's 312. That's weird. Okay, so clearly the profits are decreasing. So let's see what they want here. What is happening to annual profit over the long run? It's decreasing, okay. And I don't know, I don't think it would decrease without bound. That would just mean it would keep going down to negative infinity, but profits wouldn't go down to negative infinity. So over the long run, the annual profit is decreasing and approaching something. So how would we tell that? the other thing too is the company is in, this is after the 7th year. How long can a company last? It's not going to last for an infinite number of years either. So let's see what they're doing in C. I'm not sure how C is answered. There's that 3 halves that I had. See, you just take this and multiply by 1,000, so I'm not sure why mine was off by $1. Okay, so then here, if you want the 5th year, you do 5 and 4. Did that. So, okay, what's happening here? Okay, we want infinite limit, okay. So apparently it is infinite. Okay, so if you do the limit as time goes to infinity, as if a company could be open for an infinite amount of time, if you do that limit for the derivative function, since this is a polynomial, a limit of a polynomial going to infinity is infinity. Polynomials just grow without bound forever. So if you get infinity for this part, infinity to the 1/7 is infinity. This part is just its own polynomial, so that's infinity. Infinity times infinity is infinity. So apparently, if you could stay open for an infinite amount of time, your profit would increase infinitely without bound. But that's kind of pointless because no company stays open infinitely. So the part C is a little weird, but also I don't know why that part A was off by $1. That's kind of strange. Maybe I'll try another one and see if it comes out the same. It might have just been one example of it. But other than being off by $1 somehow, that was the only thing wrong with this one. This was off by $1. And I don't know why, because mine actually had a 0.4 at the end, not a 0.5. Pollution from factory is entering a lake. Okay, we have this derivative function here for pollution. Can the factory operate for 5 years without killing all the fish in the lake? So if you want to be there for 5 years, that's going to be the integral from 0 to 5 of the derivative function. This will let you know how many fish you're going to kill. So the function is 105 t to the 5 halves. So there's the constant. I can just ignore to the end. Increase the exponent by 1, which would be 7 halves, and then divide by 7 halves. And then evaluate from 0 to 5. And I can flip this around and make it 2/7. So 105 times 2 is 210. 210 over 7, which that might divide by 7 actually. It's 30, I think. 210 divided by 7 is 30. Yeah. So 30 t to the 7 halves from 0 to 5. So we need big P of 5 minus big P of 0. Big P of 0 will be 0 because 0 to any power is 0 times 30 is still 0. But 5 to the 7 halves, 30 times 5 to the 7 halves is probably going to be some decimal. So 5 to the 7 halves, 5 to the 7 halves times 30 is 838.254,916. So if we round that to the nearest whole number, we would kill 8,385 fish in the lake over the first 5 years with pollution, as if the planet's not already in bad enough shape. Now we're going to kill all these fish. The ecologists estimate that the lake can accept a total level of pollution of 8,200 units before all the fish are killed. So if we go over 8,200, we kill all the fish, and we did go over it. So 8385, this would kill all the fish. So 0 to 5 of 105 t they want you to set it up first, to the 5/2 power. That's the integral to calculate first. The factory cannot operate for 5 years without killing all the fish, because the value of the integral is 8380, what did I say? 8385, which is more than the 8200 that the lake can handle. Okay, so that one was better. I'm still not sure why this was off by $1, but let's try another one maybe. So number 11, part A was the only part I got wrong, but it was only off by $1, so it was something in the rounding that caused it to be wrong. So we need an integral from 0, first 5 years this time, first 5 years, 5t plus 20, and t squared plus 8t plus 3, to the 1/5 power again. So u equals the parenthesis part. The derivative of that is 2t plus 8. And again, this will be the same 5/2 at least for me. The one example they did, I think they had a 3/2 in one of theirs, but it would take an extra 5/2 times 2t plus 8 to equal the original 5t plus 20. So the only thing different about this version is I have a 3 here instead of a 1. But I've got a 5/2 extra constant that can be pulled out to the front. The u to the 1/5 will be from this part, and then the remaining part is where du is coming from. So again, I'm going to get 5/2. Let me plug the stuff back in for u right now. T squared plus 8t plus 3. And then increase that by 1 to 6/5. Divide by 6/5. So then I have to multiply by 5/6. So there's your 25/12 again. T squared plus 8t plus 3 to the 6/5 power. This is the antiderivative right here. And if we evaluate this from 5 to 0, 5 to 0, so for 5, we're going to get 25 plus 8 times 5 is 40 plus 3. The inside of the parentheses 68. 68 raised to the 6/5 power is a messy decimal times 25/12. And see, at this point, if I multiply by 1,000, the big F of 5, or big P of 5 maybe, big F of 5 is 329,434.7876. So maybe they're rounding it right at this point. That may be where I went wrong. So minus F of 0. F of 0 is nice because it's just going to be 3 to the 6/5 power times 25/12, and then multiply by 1,000 to turn it into thousands of dollars. So minus 7785.818373. Usually the best thing to do is not round anything to the last step. So 329,434.7876 minus this answer. So I just got 321,648.9692. So then this 8 would round up to a 9. So let's see if that's right now. 321649. Yes, okay, so that's what it was, is don't round. See, sometimes you have to get these wrong to see what they want exactly. The last time I did it, I was rounding too soon. As I got each answer, I rounded them, and that caused it to be off by $1. So I did the front half and I rounded it, then I did the back half and I rounded it, and then it caused it to be off by $1. So don't round anything. Do big F of 5, and a graphing calculator is the best thing, or even a scientific calculator, but you have to do big F of 5 in its entirety, leave it as a big, long, messy decimal. Multiplied by 1,000 to turn it into thousands of dollars, but leave it as a long decimal. Big F of 0, it actually came out messier this time than the first time when I had a 1 right here, but still I did it in a calculator, left all the decimals there, then subtract, then on the final step is when you round. Otherwise it can be off by $1. So that was the only mistake I made. It was just a rounding error. When you do this one, this part I did right. I just had the part A part wrong, but I got part B right after I was told what part A was. For the 6th year, you just do the same integral as part A, but you go, instead of going from 0 to 5, now you're just going to go from 5 to 6. Whatever year they want, you do it from the year before to that year. So the 6th year, you'd go from 5 to 6. And it's because year 0, you're really going from 0 to 1 in the first year. There is no year 0. So in your first year of operation, it would be from 0 to 1. So whatever year you want to do it, the year is the last number, the higher number. So year 5 is going to end at 5, and it's going to start at 4. So that's how you do part B. But now that I corrected my part A mistake, and I didn't finish the rest of this, but if I'm happy with a 97, then I can just leave this alone. I know that I did everything right now after I made that rounding error. But then if you wanted to get 100, I would have to finish part B and C. Although C is easy, you're just going to click that it's infinite profit. If you can keep your business open for an infinite amount of time, then you're going to make an infinite amount of profit, which I guess kind of makes sense. But none of us live for an infinite amount of time, so it's kind of a pointless question. But that is section 7.4. And even though I didn't get 100, I'm very close to 100 on it. And that's good enough for me. So if you're happy with a 97, that's fine too. Okay, so we have one section left to learn. That'll be the first thing next week will be 7.5. And then the second thing next week will be the review for test 4. And then December 9th is when all these homeworks and the review are due. And that's also when that extra assignment for the related rates is due. 3 students have already turned theirs into the Dropbox of D2L, so I know that's working at least. So once you get yours written out on paper, just scan it and drop it in that box in the D2L. If you have any issues uploading it, just let me know, and maybe you could email to me or something. But I guess they said the easiest thing is if you just drop it in that little D2L Dropbox, and 3 people have already done it, so apparently there's no issues with it. And then the week after that, we're going to be reviewing for the final. The review for the final has 30 questions. So I'm planning on doing 10 problems per day for 3 videos. I'll have a review video for Monday, a review video for Tuesday, a review video for Wednesday of the review of the exam week. And then you'll have Thursday and Friday, either day, to take the final. So there'll be 3 review videos, 10 problems each for 3 days. That can break it up a little so you don't have to do it all in one sitting. And that way you get 3 days to review, and then you can have 2 days to study and take the final. So we're almost done with the semester. We have 1 regular assignment left and 2 reviews remaining, and the second review of those 2 will be done in 3 parts.